In our last explainer, we took a deep dive into SIMD. Today, we're tackling something a little different, one of the most maddening, pull-your-hair-out bugs you'll ever find in high-performance computing.
Okay, let's dive right in. Picture this. It's a scenario that keeps even the most experienced developers up at night. Your code is perfect, the logic is totally sound, but your simulation, it fails. The results are just wrong. This is that ghost in the machine we're talking about. Non-determinism. It's a total catastrophe.
So what makes this so maddening? It's the fact that the bug doesn't seem to be in our code. I mean, if the logic is perfect, where do you even start to look? Well, the answer isn't on the surface. We have to go deeper, into the CPU's hidden rulebook.
You know, when you fire up a debugger, you're usually looking at the general-purpose registers, right? The RAX, the RBX, the stuff on the surface. But that's not the whole story. Underneath all that, there's this hidden layer of control registers, and these are the things that dictate how the CPU actually behaves. This is exactly where our ghost is hiding.
And right at the heart of this whole mystery is one specific 32-bit register. It's called the MXCSR. Honestly, you can think of it as the master rulebook for all floating-point math on the chip. It controls literally everything, how numbers are rounded, how errors are handled, the whole shebang.
And here's the really wild part. Just a few bits in this one register can completely change the outcome of your calculations. Take a look at bits 13 and 14, for instance. They control the rounding mode. So depending on how they're set, a number like 1.9 could become 2.0, or it could be chopped down to 1.0. That's a massive difference, and it all comes from a single tiny hardware flag.
And it doesn't stop there. Another key part of this register is the exception masks. You see, in something like a game engine, you really don't want to crash just because of a tiny math error, like a division by zero. So developers will often mask those errors, basically tell the CPU to just ignore them. The game keeps running, which is good, but it means errors are happening silently in the background, just waiting to cause bigger problems down the line.
Okay, so we've got these hidden dials controlling our math, right? But how in the world do they get set to the wrong values without us even knowing? Well, the problem isn't a bug in our code. It's something that happens between chunks of our code running, a really dangerous thing called state bleed.
The real villain here isn't a bug in our code. It's actually a feature of the operating system, something called lazy context switching. It's designed to make things faster, but it has some seriously nasty side effects.
So this laziness is what opens the door to a nightmare scenario called thread poisoning. Imagine you have a rendering thread, right? And it sets a custom rounding mode to speed things up. Then the OS decides to switch tasks. It pauses the rendering thread and starts up, say, your physics simulation. That custom rounding mode, it just boop, bleeds over. The physics thread inherits this state it never asked for and knows nothing about. It's been poisoned. And this is a perfect example of the butterfly effect in action. The physics thread expects normal, default math rules, but now it's working with a poisoned state. A tiny, tiny rounding difference in one single calculation might not seem like a big deal, but when you do that millions of times a second, the whole simulation starts to drift, slowly at first, then dramatically. This is exactly why networked games desync and complex replays fail. The engine isn't broken, it's just subtly wrong.
Okay, so we've found the culprit, the OS and its lazy context switching. So what's the fix? Well, it's pretty clear we can't trust the operating system to handle this for us. We have to take matters into our own hands and seize direct control.
The solution is to go around the OS completely. We're going to establish a direct contract with the hardware itself. We'll use special assembly instructions like FXSAVE and fxrstor to manually force the CPU into a clean, known good state, every single time.
So what do these instructions do? Well, FXSAVE is incredible. It takes a complete snapshot of the CPU's floating point environment, all the registers, including our critical MXCSR, and saves it into a 512-byte block of memory. But there's a catch, a really important one. That memory must be 16-byte aligned. If it's not, the whole thing just fails.
All right, so we've got the tools. We can save and restore the CPU state. But how do you actually use this in a big, complex, multi-threaded engine? You can't just sprinkle these instructions everywhere. You need a proper architecture. And that's where the clean room solution comes in. So here's how we build this clean room. In a modern job system, you have a bunch of worker threads, right? We give each and every one of those threads its own private 512-byte chunk of memory, a scratch pad. This little scratch pad acts like a sterile environment, a personal lab where that thread and only that thread can save and restore its state.
This creates total isolation, and we enforce it with a really simple discipline protocol. It goes like this. When a thread is about to start a new job, first thing it does is load a sanitized default CPU state. If the OS interrupts it, no problem. It just saves its current in-progress state to its private scratch pad. And when it's time to resume, it loads that state right back. Simple. And just like that, state bleed is gone.
And by following this simple contract, we've completely eliminated the root cause of the non-determinism. We're not trusting the OS anymore. We honestly don't even care what the last thread was doing. We own the state now. And that means we finally have true, reliable stability.
So, what's the big takeaway? I think it's that sometimes the nastiest bugs aren't in your code at all. They're hidden in the assumptions you make about the hardware and the OS running underneath it. It really makes you stop and think, right? If the OS can't be trusted for something this fundamental, what other efficient behaviors might be silently messing with your application's stability?
Definitely something to chew on. Happy coding!